Good morning, ladies. So, oh, there's Callie. How was everyone this morning? Okay, good. I'm just happy it's Friday. We're good. So good. So it's kind of reminding what we talked about yesterday. At the very end was combining resistors. So again, here we're taking a collection of resistors and adding them together to create new resistances. So either we want to increase or decrease the overall resistance, so we can combine them in parallel. And just remember that when we combine them in parallel, each one of the resistors has exactly the same voltage across them or potential across them. So we add those guys inversely. And then for series, we simply add them together and they have exactly the same amount of current which is running through those. Okay. The overall effect, again, is when I add them in parallel, that decreases the overall resistance. If I add them in series, that increases the overall resistance. And basically one thing to kind of point out is that all of this comes from mostly here, right? Because remember that resistance is resistivity times the length divided by the area. So when I add resistors in parallel, so let's say if I add these guys in parallel, so they're all kind of hooked up in parallel, you can kind of think of this as what? Making one big resistor whose cross-sectional area now becomes much bigger. Right? So the effect of adding all of these together is to give me something which has a much bigger cross-sectional area. So if I increase the area, I decrease the overall resistance. Right? So that's basically what's happening here. Where if I take resistors and I add them in series, so in this case, I'm combining all these together to create a resistor. If I knew how to draw, my life would be better. There we go. Whose length has now increased, right? So now I'm just adding all these guys together with a much longer length. So the length has now increased. And since the length is increasing in that case, then the overall resistance is increasing. So this is basically where the effect has come from. So when they're parallel, you're effectively increasing the cross-sectional area. So in that case, you're decreasing the resistance. And when you're adding in series, you're now increasing the overall length, which now increases the resistance. So, as I promised yesterday, we're going to start off with actually a group assignment. So here is our group assignment we're going to start off with today. So this has, we have a 12-volt battery. Somebody else is coming on. Yeah, go ahead. So we have a 12-volt battery connected to 4 resistors as shown below. So basically what's happening here is what? We have the battery attached here. So initially this switch is open, which means that this wire is basically not there. Okay? So since that wire is not there, since that switch is open, what that means is that R1 is in series with R2, R3 is in series with R4, but R1 and R2 together are in parallel with R3 and R4 together. Okay? And then these are the different resistances. So in this case, what we want to do is calculate the equivalent resistance and the current flowing through each of the resistors and the potential across each resistor when the switch, again, is open. Okay? Now again, since these two are in series, that means they have to have the same current. These two are in series, which means they have to have the same current. But these two together are in parallel with these two together, so these two together have exactly the same potential as these two together. Then part B is now saying, okay, so now we're going to close the switch. Doesn't really want us to do any calculations, but it wants us to determine how these quantities are going to change. So meaning, is the equivalent resistance going to go up or go down based off of what we know about resistors here? So what happens is now when I close the switch, what's happening now is that, what? 1 and 3 are now in parallel, 2 and 4 are now in parallel, but 1 and 3 together are in series with 2 and 4 together. So by closing the switch, you're simply changing the geometry. Once you change that geometry, then that changes the overall resistance. Okay. So for part A, all of this here is just written in part A. So here you should find that the equivalent resistance is 21 ohms. And as I said, current through 1 and 2 have the same current, so that's 0.4 amps. 3 and 4 have the same current, so that's 0.17 amps. And then these are all the different potentials across each one. So I'll let you guys work on these. I'll give you about, I don't know, 15, 20 minutes to kind of work on those, and then we'll start talking about adding capacitors in parallel and series. And they basically do all the same stuff. Life will be good. Okay. So good. So we'll do 2 rooms, and I'll have you guys split up. Okay.
I just don't know at what point do you add the, like, I don't know. I'm confused on it still.
So how are we doing so far, ladies? I heard we're confused.
I'm drawing it so that Callie can see it since she can't pull it up online
My
right now.
computer's dead, so.
Oh, really? Sorry. Gotcha. Here. Let me share my screen. No. You can see it. Okay. There it is, Callie.
Thanks. What the heck?
Like R1 and R3 together.
Little phone zooming.
R3, R4. There. Now I have it drawn at least so that when Professor Greenwood leaves, you can still see it.
Great.
Callie, is your email open?
My email?
Yeah, I mean, I can email it to you too.
Oh, yeah, that'd be great.
Okay.
I'll just switch screens in and out from the Zoom.
Okay. Yeah, let me, I'll email it to you real quick.
Thanks. And Katie has it drawn as well, so that's good.
Oh, not nearly as beautiful as the computer drawn diagram, but it will suffice.
Oh.
Yeah, it's a lot of hard work drawing those things. So let me think.
I did a couple of lab reports in Physics 175 where I was trying to draw with the tools on the computer, the little arrows and stuff, and I was just like, oh my gosh.
Yeah, it
this is
takes
so
forever.
frustrating.
Yeah, it takes forever, but it's all right. Especially when you're trying to draw the squiggly lines for the resistors.
Oh my gosh, I'm sure.
Okay, so I just sent it to you, Callie, so you should.
Cool,
have
thank
it here in
you.
a second. All right,
So
Yep.
we know resistor 1 and 2 are in series for A, and we know 4 are in series. So I want to like write R12 plus R34, but I don't know at what point. I get confused. At what point do you start adding in, like, breaking it down into like potential and current and all that stuff?
Oh, that'll be after you put everything all the way down into an equivalent resistor. So the first thing you have to do is find that equivalent resistance. So you want to combine everything down first, and then as you're unraveling what you just did, that's when you want to start looking at potential and all that good stuff.
That way.
So
That's right. So what Katie has drawn is correct. That's right. So first you're combining 1 and 2 together, and then 3 and 4, right? Yeah.
I cannot. Sorry.
Trying to see things on the phone. Yeah.
Yeah, it's super annoying. Sorry.
And there's like, I'm sorry, there's such a glare from my computer like back on the whiteboard.
You're fine. So that's right. So you're adding the 2 in series together. So the top 2 in series and then the bottom 2 in series. And then once you have those in series, so to create the new ones, then you add those together in parallel. to then create your REQ.
Yeah.
That's right.
So I actually attempted this last night, and I think I got all of the currents that you got, and then I just stopped there for the night. So I think I've got a good start on
Good.
it. Yeah.
Nice.
All right.
Okay. So let me check on the other group, see how they're doing.
All right. Sounds good.
Series, because that's what he did. But I don't know how you can just like crash those down, because technically it's like R12 and R24 first. So don't we have to find R12 before and R24 before we can find those?
Yeah, you can do it that way. So R12, since they're in series with each other, you would just add the two resistors together. So that means R12 is equal to R1 plus R2, which would then just be 30 ohms. And then R34, which is R3 plus R4, would then just be the two resistors added together. So that's going to be 30 plus 40, which is then 70.
And then would you go and find like REQ, and that would be like when you had them in parallel?
Correct. That's right. So now you're adding 1 over 30 plus 1 over 70. That's right. And then you have to invert that back to get actual REQ. But that's right. That's absolutely right, Taylor. That's right. Exactly.
Resistances, are you just adding, like R1 and R2 are combined, so do you just add those
Yeah.
together?
They're in series. So what I did first was I decided that, like, I did the series ones first. So I said R12 is equal to R1 plus R2, and then R34 is equal to R3 plus R4. And I calculated those separately because for me that works better. I stay more organized if I don't try and plug whole things. I like to find that number first and then move it if I can, because then it's just one less term for me to try and keep track of as I carry it down.
Yeah.
And then I
just
plug
like to be
those
as lazy
in.
as possible and do everything at one time, but it's fine.
I can't do that. I start dropping terms just as I'm carrying things down, and I'm like, wait, that was squared. No wonder I lost that 3 lines ago.
Yeah. Unfortunately, that happens. Yeah.
Yeah, it happens to me a lot. I just can't keep track of it. So if I have a number I can plug in and just find a number, that's better for me.
There you go. That's right. Yeah. So R12 will just be 30 and R34 will be 70. So just the sum of those numbers. That's right. And then your REQ
And then
will
you
be
would have something.
the adding the inverse of those together. So that's going to be 1 over 30 plus 1 over 70, and then invert that to get REQ.
Mm-hmm.
Very good.
You said invert that after you do it?
Yeah, because you're adding 1 over, so because that's 1 over REQ. So to get REQ, then you have to invert that whole thing after that. That's right.
So I get 0.048.
Good. Now take the inverse of that.
So it'll be like 1 divided by that answer.
Yeah. So 21. Okay.
There you go.
But I got 2.
Yay.
It's always exciting when you get the right answer.
That sure is.
Yep. I'll be like solving things, and then I go back and check at the end, and I'm just like, yes.
Yeah, it's always a big accomplishment. That's right.
In physics, for me anyways, I'm like, physics is hard for me. The math is hard for me sometimes. So
Mhm.
just like, if I get the same number that you got, especially on the first try, I get really excited.
Yeah. Physics is definitely not for the faint of hearted. We'll put it that way.
No, it is not.
You just got to celebrate those little wins. You're like, first try, hooray.
Exactly. Exactly. All right, I'll be right back. Let me check on the others.
Okay.
Q times REQ. So then you have delta V equals REQ over to find that. I think that's because does it give us the voltage of the battery?
Yeah, it gives us the 12 volts.
What would that be? Hold on. I'm gonna see.
So would it be?
How we doing, ladies?
I think okay.
Now here, so notice one thing, we actually don't have to calculate IEQ. And the reason we don't have to do that is because R12 is in parallel with R134, which is also in parallel with the battery. So basically what that means is that the potential across 1 and 2 together is 12 volts, and the potential across 3, 4 together is also 12 volts. So since all of those things are all in parallel, then they all have to have exactly the same potential. So this is one of those cases where we actually don't have to find IEQ because it's not coming from two things which were in series, but two things which were in parallel. So as long as they're in parallel with each other, then the potentials have to be the same. So that means that you know now the potential across 1 and 2 together and the potential across 3 and 4 together. And now you can use that to find the current through 1 and 2 and the current through 3, 4.
So to do that, we would just take like the 12 volts divided by R12.
Exactly, yeah.
Okay.
Yeah. So it's just gonna be 12 volts divided by 30. Exactly. And then to get the other one, you just take the 12 volts divided by 70, and then that would give you the other current. And now, since 1 and 2 were connected in series, that means they have to have the same current, which is exactly that same current that you found through 1 and 2 together.
And then 3, 4 would be the same thing.
Exactly. So the current through 3 and 4 together is exactly the same current as in 3 and 4 separately, because again, they're connected in series. And now, since you know the current and you know the resistance, now you can find the potential across each individual one. Okay. Good. Very good.
Let's see, what did I use?
It's me again. How we doing?
Hi. We're working on the currents.
Okay, good. Now here, notice that you actually don't have to find IEQ. And the reason you don't have to do that is because R12 together and R34 together are both separately in parallel with the battery.
Mm-hmm.
So since...
I did anyways, but just a little extra work for me. I wanted to fill in all the
That's
blanks.
okay. It's okay. But since each one is in parallel, then what that means is that we know the potential across 1 and 2, that's just the same as the battery, which is 12 volts.
Right.
Across 3, 4 is also the same as the battery, which is 12 volts. And then the battery has the 12 volts. So as long as REQ comes from two things which are in parallel, you actually don't have to find IEQ because you already know the potential
The voltage
to
is
be
the
the same
same.
as that of the battery. That's right.
Right.
But if it came from two things which are in series, then you do have to find IEQ because IEQ would be the same as what's coming out of the battery in that case. So the currents through each one.
When we were doing these in lab, I found a YouTube video where I was trying to learn how to do them. And he just made a list of like, so REQ, R1, R2, R3, and then like the same thing for voltage and the same thing. And that helped me a lot. So I just make a list of what I have and what I don't, all of it in a row, and then I find everything.
Gotcha.
So I just found IEQ because it was a blank and I wanted to fill it in.
That's fine. Nothing, never ever hurts. It's fine.
I'm okay, but so now I'm confused a little.
Sure.
about finding the voltages.
Oh, for the voltages, so now once you find the current, so the current through R12 is the same as the current through R1 and the current through R2 since they're in series.
Wait, the current R12 and R34 are in series, so the current is the same.
Well, no. So R12 came from two which were in series, which was R1 and R2.
Mm-hmm.
So that means the current through R12 is the same as the current through R1 and through R2.
Oh, okay.
Same thing is true for 3-4. So the current through R34 is the same as the current through R3 and the current through R4 because those are in series.
Mm-hmm.
So now that you know the current through R1 and you know the resistance of R1, now you can find the potential using Ohm's law.
Okay, so that was given to us.
Yeah,
Go
that
back.
was a 10, I think. So R1 was 10. Yeah.
Oh, okay, I see. So you don't only have to do it like once for R1 and then once for R3.
Right.
Because the other two would follow up. Okay. Okay.
Okay. And as a good check, since you know the potential across R12 is 12, then the potential you get across V1, or the potential across 1 and the potential across 2 have to sum to 12. The two of them together have to add up to the same amount of potential.
I know you said the currents were the same for, so R12 is the same as R1 and R2, but how do you calculate that current in the first place? Like, I'm missing that step.
Oh, so again, what you know is since R12 together is in parallel with R34 together, which is in parallel with the battery, that means all three of them have to have the same potentials.
Is that what you're talking about?
That's
Like
right.
this math?
Exactly. So what that means then is you know the potential across 1 and 2 is 12. So that means the current across 1 and 2 is then going to be 12 divided by the resistance R12. So in this case, it's going to be 12 divided by 30.
And then R34, because it's in parallel with that.
Also
I'm sorry.
has that 12 volts.
Series,
No, R34 is in parallel. You were correct the first time.
that makes the current the different.
Correct. That's right.
Okay, this stupid little. I don't know why I keep getting confused. Okay. I.
Resistance just be small.
It'd be less than. It'd be less than, right?
How we doing?
That's what I would think.
We're trying to figure out part B.
Okay. So I heard Tara say less than. So does everybody agree with less than?
Well, we kind of just got to that point because we saw it had low. Like we looked and saw that when you have that resistor has like low current and all that. That makes sense.
Well, the answer is less than. That is correct. And Tara, why do you think that?
She was just talking about when it's open that it tends to be lower, and that was one of the options. So it seemed to make sense.
See, good. So when it's closed, what's happening is now you're adding two separate things in parallel as opposed to two things when it was open in series. So remember, when it's in series, that increases the resistance, but when it's added in parallel, that decreases the resistance.
Yeah.
So the difference is when it's closed, you're now adding 1 and 3 together in parallel with 2 and 4 together in parallel, which means that you're decreasing your overall resistance. instead of 1 and 2 together, which is now adding, with 3 and 4, which is adding, because they're in series. But, so here we should expect the equivalent resistance to be less, because now we have them in parallel as opposed to in series. And then if you want, you can go through and actually calculate it and prove to yourself that it actually is less. Not gonna be hugely less, but it'll be less. So, but only if you want to. I'm not gonna make you do that. Very nice. Good job, ladies. Very good. All right, let me check on the other group.
Okay.
All right, how we doing?
I think we're mostly finished. Callie, how are you? Oh,
Sorry,
did we lose her?
I'm just finishing up
Maybe we lost
finding
Callie.
I'm right.
Oh, she's here. I can just you're delaying a little bit, so I think that's
Okay. Yeah, I'm just finishing up getting those voltages.
good.
Okay.
And what do you think for part B? I didn't give you the answer in part B, but what do you think? So the difference now is you're closing that switch instead of leaving it open. So you're again changing the geometry. So how would that affect? So what do you think? Is it going to remain the same or increase or decrease based off of what we know?
When you make something in series, you increase the resistance, but
Correct.
they're still both in parallel with each other. So I would think that it's going to turn out to be pretty close to the same.
It'll be close, but again, in which way? Is it going to be close higher or close lower? So it won't be the same. It's not going to be exactly the same. But what do you think is the difference? So the difference is initially when you add them, you're adding what? 2 in series and 2 in series, right? So you're doing 2 series additions with 1 parallel, right? But now when you close the switch, you're doing 2 parallel with 1 in series.
2 parallel additions with 1 series.
That's right. So what should that
So
do?
it would be lower.
It should be lower. That's right. So what should happen is the overall equivalent resistance should now decrease because you're adding 2 in parallel. So 2 separate parallel calculations, which we know are going to reduce the overall size of the resistance, and then doing 1 series addition on top of that. So that's right. So overall, it should decrease. It should be lower. Okay, it probably won't be lower by that much, but it will be lower.
I calculated it as 20.8 ohms. So it's 0.2 ohms less.
That's right.
So it's very close.
It is close. But yeah, but still lower at the end of the day. So very nice. Good.
Yeah.
Let's do this. All right, so I'm going to bring everybody back so we can start
Okay.
capacitors. All right. All right, welcome back, ladies. So sounds like everybody did a good job. Looks like, did we lose somebody? Well, we'll figure it out. Maybe just have them come back in. All right, so the next thing we're going to start talking about is keep it on the same thing, but now we're going to add capacitors in parallel and series this time. So we want to basically do the same thing, but now we're going to do it with capacitors. So we want to add capacitors in parallel and series. Again, we already did this in lab, but again, we'll do it kind of formally. See how this works. Okay. So again, the reason we want to do this is for the same reason before, is that, again, where you can only manufacture certain numbers and certain capacitances. So we want to create new capacitances, and we have to add them in parallel and series. So let's look at, which one do you want to do first? Katie, which one do you want to do first? You want to do parallel or series first?
Let's do parallel. Why not?
Parallel first. Okay, so here is, let's tell that C1 and put C2 here, and down here will be C3. Okay, so C1, C2, C3. Good. So again, we're going to connect this to a battery, delta V. So there's my delta V. Now, what's different between capacitors and resistors is that there's actually no current. So what'll happen is initially you're going to run current, and we're going to talk about this either tomorrow or on Monday. But what happened is initially there's going to be current running through the system until eventually the capacitors fill up with maximum amount of charge. Once that happens, no current then runs through the system. All that's going to happen is each one of these is going to have a maximum amount of charge. So what'll happen then is that this will have a charge of Q1. So this side will be positively charged. This will be negatively charged on this side. This one will have a charge of Q2, where again, whatever's closer to the battery will be positively charged. Further away is going to be the negative charge. And this one's going to have a Q3. So it's going to be positively charged and then negatively charged. So, but again, each one of these are in parallel, so we know what has to be true is that the potential across C1 has to be the same as the potential across C2, which has to be the same across C3, which is all equal to that of the battery in this case. Now, the claim again is that we can combine all of these down to then create an equivalent capacitor, so that now we have one capacitor, CEQ, connected then to the battery. So this is our battery, delta V. Here's our CEQ. And what's going to happen then is that the top plate here is going to be positively charged. The bottom plate is going to be negatively charged, but this is going to have a total charge of Q. Now again, what has to be true is that the charge which is coming out of the battery, Q here, has to equal the sum of all three of these charges. And that again is just going to be conservation of charge. So conservation of charge tells us that the charge on the equivalent capacitor here must be equal to the sum of these three charges. Right, so whatever charge builds up on C1 and C2 and C3 have to sum together to equal that of the battery. Now we also remember that we have Q is equal to the capacitance times the potential, which means that for him, we can rewrite this then as the capacitance, which is the equivalent capacitance times the potential across the battery, must then be equal to the capacitance C1 times the potential across that capacitor, plus C2 times potential V2, plus C3 times potential V3. Or, since all those potentials are the same, that's going to be C1 plus C2 plus C3, all times the potential. Now again, the potential from the battery is the same as potential across each one of the plates. So finally we get that CEQ is equal to the sum of all the capacitors. Or in general, this is going to be equal to the sum over I of all the capacitances. So here, what's happening now is when I'm adding capacitors together in parallel, they add directly together, unlike resistors. Remember, resistors in parallel, these guys added inversely. So this is just doing the opposite. So with resistors, adding them in parallel had the effect of decreasing the resistance. Well, with capacitors, it actually has the opposite effect. It actually increases the capacitance. And yeah, the reason for this is, remember that if this was a parallel plate capacitor, the capacitance of a parallel plate capacitor is epsilon naught times the area divided by the distance d. So we said if we add them in parallel, that's effectively increasing the area. So what we're doing is we're increasing the area, which is, again, increasing the capacitance. So again, here we're increasing the area. Which then increases the capacitance. Okay. So anytime I have capacitors in parallel, I'm simply going to sum all those guys together. So this is my CEQ in parallel. And again, parallel, what that means is that what? All of these have to have exactly the same potential. So potential is the same. Always okay? Not too bad. So then we want to add them in series. So go to a new page. So now in series. So again, here's my battery. I'm going to connect that to C1. Just connect it in series to C2. Connect it in series to C3, which is then connected back to our battery. And again, what we want to do is collapse all of these guys down together so that all of them are connected. So the battery is connected directly to CEQ. So this is my delta V, and this is my delta V. So again, what's going to happen is whatever plate is closer to the battery become positively charged, which means the one further away become negatively charged. So this is also positively charged, negatively charged, positively charged, and negatively charged. Now, conservation of charge tells us that whatever charge comes out of the battery has to be the same as the charge on each one of these different plates. So that means this plate will be positive charge Q, this will be negative charge Q, positive Q, negative Q, positive Q, negative Q, but all these charges are the same which comes out of the battery. So in series, these all have exactly the same charge. Again, this is just conservation of charge. Now, much like a resistor, a capacitor also creates a potential drop. So what'll happen is as the charge comes out through the battery, I have a potential drop across this capacitor, which is going to be delta V1. I have a potential drop across this capacitor, which is then delta V2. And I also have a drop of potential across this capacitor, which is then going to be delta V3. Now, conservation of energy tells me that whenever potential is supplied by the battery, I have to then have the same amount of potential drop throughout this entire circuit, which means that this potential here for the entire thing has to be the same as that of the battery. So the sum of these three potentials has to equal that of the battery. So the potential drop across CEQ has to be then the sum of these three potential drops. So this tells me that delta V across the EQ then must be equal to delta V1 plus delta V2 plus delta V3. So again, just like a resistor, the point of having a capacitor then is to have a potential drop. So I have to lose potential due to the fact that I'm actually storing charge. So I'm storing charge, I'm storing energy, so it takes work to do that. So I create a potential drop due to the fact that I'm storing that energy. So good. So again, using that Q is equal to C times delta V. This means that delta V is then going to be equal to Q divided by C. So that means this is going to be Q divided by C1 plus Q divided by C2 plus Q divided by C3. And on this side, this has to be then Q divided by CEQ. Again, our claim is that these two things are the same. Now again, the charges are the same because they're all in series, so we can cancel out all those charges. So what this says then is that 1 over the equivalent capacitance then is equal to 1 over C1 plus 1 over C2 plus 1 over C3, or in general, the sum of the inverted, or the sum of the inverses is 1 over CEQ. So again, when we had resistors, we added resistors in series, we simply added them together, but now that we're adding them in for capacitors, we're doing the opposite again. So what this means then is, when you write on, say, your equation card when you're getting ready for the exam, or if you memorize these, just remember that the capacitors are opposite of what the resistors are. So basically, if you write that, you know, if you have series for resistors and you write this as simply the sum over the resistors, and then for parallel, you write this as the sum over 1 over. So just remember that capacitors are the opposite for capacitors. Or in case you don't want to forget that, you can write everything down. That's up to you as well. I'm not going to tell you not to do that, but just know these things are the opposite. And again, the reason for this is now when I'm adding them, in series, again, I'm effectively increasing the length. And again, if we go back, we know that for parallel plate capacitors, this is dependent inversely on the length. So if I increase the length, I decrease the capacitance. So the overall effect of adding these in series is to decrease capacitance. So this decreases capacitance. And this happens by increasing the length. So increasing D. So good. So let's do an example using these. So this example is, so let's look at this circuit here. So this says that we have the circuit where we have C1, C2, and C3, which we're going to take to all be exactly the same capacitance, which we're just going to call C. So it means C1 is equal to C, C2 is equal to C, and C3 is equal to C. And we want to know what is the equivalent capacitance of the circuit, and then what is the charge on each of these capacitor plates. So how much charge do we have? So this is the example we want to look at. So let's redraw this. So good. So we draw in blue. So here is my battery, delta V. And I'm going to connect that then to these two. So here is C2 connected then with C3 in parallel. And then that's connected to C1, which is then in series with that, which is in series with the battery. Oops. So good. So again, first thing we want to do is find what is connected to what and how. So first thing we know is that C2 and C3 are connected in parallel. So we know these two were in parallel. Then if we combine those two together, what we know then is that C23 together with C1 is then in series. So the first thing we want to do is connect C2 and C3 together in parallel. So we're going to redraw our circuit then as what? This one together, which is then C23, connected now in series with C1. There's that guy. And then we want to combine these two together in series to then create finally CEQ. So this is our CEQ. This is our delta V and our delta V. Good. Always okay? So now let's do some calculations. So first of all, we know that C23 came from two capacitors in series, and how do we add capacitors in series? So do we add them inversely or directly?
Inversely.
Almost.
In parallel or series? I'm
In
sorry.
parallel. So capacitors.
Oh, yeah, then it's just directly.
Good.
I thought you said series. I'm
You're fine. So good. So since these came in parallel, we know we have to add them directly. So this is going to be C2 plus C3, but we know C2 is equal to C3, so this is just going to be twice of C. Right? Because remember that C1 is equal to C2, which is equal to C3, which is equal to C. So even though I'm adding C2 to C3, but they're both equal to C, so that's just 2 times C. Good. So then CEQ comes from two things which were in series. So this is now going to be what? 1 over C23 plus 1 over C1, which means CEQ then is going to be equal to C23 times C1 divided by C23 plus C1. So I've written this down a few times. Just be a little bit careful with this, because if I had, for example, 1 over CEQ was equal to, say, 1 over C1 plus 1 over C2 plus 1 over C3, this is not the same as CEQ is equal to C1 times C2 times C3 divided by C1 plus C2 plus C3. This is not the same, so just be careful. So here I'm just doing algebra to get this here, but this is not true. So just don't be tempted to do this, okay? And one way you can see that is because this goes as capacitance cubed divided by capacitance, which means this goes overall as capacitance squared. So you then would have capacitance is equal to capacitance squared, which is not true. Okay, so just be a little bit careful. So just don't think this always works, but for two capacitors, this is fine. Okay, so good. So this is going to be the same thing then as 2C times C divided by 2C plus C, which is the same thing as what? 2C squared divided by 3C, which is the same thing as 2/3 C. So the equivalent capacitance for this is 2/3 of C. It's okay. Let me get rid of this. I need that room. Good. So now we're going to get the charge. So now once we get here, we go backwards again. So now let's go backwards. So going backwards, what we know is that what? CEQ came from two things which were in series. And what's the same in series? Is it potential or charge?
Charge.
Good, Taylor, charge. So we know is that what? The charge on here is going to be the same as the charge on here, which is going to be the same as the charge on the equivalent capacitor. So from here, we're going to calculate the equivalent capacitance. So we know the equivalent capacitance then, or sorry, the equivalent charge is going to be equal to the equivalent capacitance times the potential across the battery. So this is then just going to be simply 2/3 C times the potential across the battery. So good. So we know then is that this is going to be equal to 2/3 C delta V, and we know the charge on C23 together is then delta, 2/3 C delta V. Good. So now we know the amount of charge which is on C1. Q1 is that just QEQ. Good. So now we know C23 was put together by two things which were in parallel, and what's the same in parallel?
The potential.
The potential, good. So here we can now calculate V23 because now we know the charge, we know the capacitance, so now we can calculate V23. So this is going to be the same thing then as the charge, so this is QEQ, divided by the capacitance C23. So it's going to be the same thing then as 2/3 C delta V divided by 2C. So the C's are going to cancel, the 2's are going to cancel, so this becomes 1/3 delta V. So it means this has 1/3 of the amount of potential. So good. So since these are in parallel, we know this has to have the same amount of potential as this guy. So now since we know the capacitances and we also know the potentials, we can now finally find the charge. So this tells me then that Q2 is then going to be equal to C2 times delta V23, which is then going to be 1/3 C delta V. Q3 is then going to be the same thing as what? C3 times delta V23, which is going to be the same thing then as also 1/3 C delta V. So just out of curiosity, can you hear my daughter when she's screaming like that or no?
Only a little bit.
Only a little bit? Okay. She is the loudest person I think I've ever heard in my life. Okay. She's only 2. Life is great. Okay. So everyone's okay? So not too bad, right? So basically the same thing, but again, the only difference is how we add them together. So again, when they're in series, we add them inversely. When they're in parallel, we add them directly. So here, instead of using Ohm's law, we're using then the one for the capacitor. So basically, it's just repeated applications of this guy. And then again, how are these things actually added together? So that brings us to our next group assignment, which is Where is it? I didn't open it. Okay, give me 1 second. I thought I opened it. And I just added this a little while ago. So if you looked on Blackboard, you wouldn't have seen it before, but now it is up. So here it is. Oh, ignore the second question. We already actually did that before. I don't know why that's there. Okay, that's fine. Let me just double check. Oh. Okay, sorry. Wrong class. Here we go. That's better. So this is that we have these capacitors, which all have exactly the same capacitance of 7 microfarads. Okay, so this one, this one, this one, and this one all have 7 microfarads. And these are connected to an EMF, where that EMF has a voltage V, which is 15 volts. Okay, so this has 7, 7, 7, and 7 microfarads. So the first thing we want to do is calculate the equivalent capacitance for the entire circuit. And then what is the charge on the equivalent capacitor? And then what is the potential across each one of these different capacitors? And then what is the charge on each one of these different capacitors? So this is what we're looking at. So randomly, so it's probably easier for you to call each one a different capacitor just to keep it so you know which one you're actually talking about. So for example, you can call this one C1, C2, C3, and C4, whatever combination that you want. Even though they're all just simply C, but yeah, again, it makes it kind of easier so you know which ones you're actually talking about. Okay. So let's talk about each one. So how is each one connected? So we can say this one here is in series with the battery, which is in series with these two combined together, which is in series with this one. These two are connected in parallel. So the first thing we would have to do is what? Collapse these two parallel into series, and then these three are now all connected in series together. So good. So once we do that, combine these two, which were in parallel, then into, now everything's in series. Now you can add all that beautiful stuff together and then do all the same stuff we just did. So good. So let's go ahead and, so it looks like that's about as far as we're gonna do. So pretty much I'll give you the rest of our class time, which is about 20 minutes. We kind of work on this in our groups here. So good. So let's do our breakout rooms and we'll open our rooms. Hello, everyone. How we doing?
Hello.
I'm going on Blackboard to get it to pull up.
Okay.
I'm taking down the given information and now collapsing my circuit down a little bit at a time.
There you go. Yeah. This one's a little trickier because now you got 3 in series. So you got to add 3 inversely to each other. So, but not too bad. Not too bad. We can do it. I have faith.
It'll be all right. Something like that. Two, three,
My daughter takes after her grandmother. We have to remind her to use her inside voice all the time, so she's just very.
Hey, healthy lungs, right?
That she does.
For farads, the farads is 1 times 10 to the negative 6.
So it's just 14 times 10 to the negative 6. There.
For the 2 in parallel, yes. Yep, that's right. Everything going okay, ladies?
Yeah.
Good. Very pleasant hearing the birds chirp in the background.
It's relaxing.
Yes, definitely.
Which makes sense because since we're adding them in series, it's going to be less than any one of them.
Mm-hmm.
It was a little lower than I was expecting it to be, but it
Yeah.
is less, so.
And then for the charge on the equivalent capacitance, it's just the 2.8 times the 15, right?
That's right. Yeah. With the micro. Don't forget the micro. But yeah. Yep. After you do that, now you get to do all the unraveling and try to figure out what's the same and what's different and blah, blah, blah. The only good thing is since C1 and C4 are connected in series, then those are the charges. So, good. All right. Check out another group. Still doing okay, ladies?
So So did you just take the CQ times 15? Right?
That's right. Yep. And then that'll be the equivalent charge. That's right. Yep. That's it.
Not a
I did
positive.
the -9. It's not negative 6. not -6, so that'll change it a little bit.
Okay.
Still doing okay?
Yep,
We're
just a
talking
unit.
about charge and then the conversion for microfarades.
Gotcha. Okay. Yeah, micro is -6. So that's all we need.
Question. There it is. Okay, potential across each.
12 volts, I think. Or 15, sorry, yeah.
Wait, what'd you get for CEQ? That's what I was talking about.
Oh, it was
Oh,
the
2.8 microfarads.
What the heck? Okay. All right, for that, like, don't you just do CEQ and then equals C1 plus C23 plus C4, and then you do C1 plus 1 over C2 plus C3, because that's C23 because they're in parallel. I'm sorry. Wait a sec. They're
No,
in series. This is opposite.
yeah, you should invert them.
Yep. There's the issue.
So now we want voltage. When they're in parallel, they're the same. So this voltage would be 2, 3, delta T, and in series later added together.
So which part are we working on now?
Part C.
I'm on part C, so I'm finding the potential difference across each of the capacitors.
Oh. So note that basically you have to do C and D simultaneously.
Okay.
So
I
you
was
can't just do the potential and then just do
like
the
I had
charge.
yeah, I had written down the rules for voltages in series and parallel first, just to make sure I didn't get them mixed up.
Yes.
And I was thinking to myself as I did that I probably wasn't going to have enough information to find those voltages just from the voltage equivalent.
Correct.
So I was probably going to have to use a different equation anyways.
Yeah, so kind of like what we were doing when we were going backwards. So again, you have to keep track of what's the same, and then from there you have to calculate something to calculate something else. So yeah, so anytime you see something like that, what's the charge and what's potential across each one, you pretty much have to do the two at the same time, even though it's asked as two separate questions, but yeah.
Okay.
So here, so again, the top one and the bottom one, you know their charge is QEQ, so you actually already know the charge. So once you know that charge, you can now find the potential.
But I don't know if it's 1 over the back.
How we doing, ladies? Looks like we lost Tara.
We're working on the potentials.
Across 1 and
So,
4.
that's right. So notice that to do the potentials and the charges, you basically have to do those at the same time. So a lot of times you'll have to find one before you find the other one. So here, what you know is that what? You know the top one and the bottom one are connected in series to the other two, which were connected in series together. So you already know the charge against the top one and the bottom one. That's just that equivalent charge that you just found. So basically, you know the equivalent charge on the top is the same as equivalent charge on the bottom. And since you know the capacitances, then you can find the potential. So the potential then is just going to be the charge divided by the capacitance. So the top one and the bottom one actually have exactly the same amount of potential since they have the same capacitance. So. And then for the two in parallel, you have to find that charge, or sorry, that potential first, and then split it up to find the two different charges. Is that okay?
So for the V2, so like for the two that are in parallel, you would just take the.
So they still have the equivalent charge because they're
Yeah.
still in series, but now you would divide it by twice the capacitance instead of just the capacitance. That's right.
Yeah, so then for the charge of them separately, you would
Good.
just multiply that by their capacitance.
Correct. So now you take that voltage and multiply by the capacitance. Correct. That's right. And then that would give you the charge. But again, since each one has the same capacitance, they'll have the same charge as well. That's right.
I don't know why, because I have conversion as 7 to the 10th times -6 as my conversion. But my answer for CEQ ended up being e to the 5th. I'm confused.
Whoa.
Probably because it was inverted and
What?
stuff. I don't know.
That's a really big. Did you convert the microfarads from the beginning?
Yeah.
Okay, that I didn't do that. That might be why you ended up with such a large number. Because I just, for the first part, CEQ, I just left it in microfarads, and then for part B, I changed it to farads because then it would matter. The first part, I was like, it doesn't really matter.
Yeah, I don't know.
Because they're all in the same unit there, and you're just adding them together.
This dog, oh my gosh, I'm gonna kill it.
Are you in, Callie, are you in the group text? You are, aren't you?
Yeah, I am.
Okay, I'll send a photograph of my math so you can look at it. It's kind of hard to talk it through.
Dude, I know. Thank you. I just
Yeah.
am getting stuck at the stupid parts.
So you should have microcoulombs and microfarads, so the micros would cancel out.
Well, we calculated. We weren't given any charges to begin with, were we?
Right, but I'm saying when you calculate them, you'll just get micro, right? Because you have to get the charge.
I just did the conversion so that it would, when I calculated the first one, it would be in coulombs.
Right. Okay. Yeah. The other way to think about it is, so you have your equivalent capacitance is what, 2.8 microfarads, and then you're multiplying that by 15. So that's going to give you microcoulombs. Right. So it's 2.8 times 15, which is how much? 2.8 times 15. So that's 3,120 microcoulombs. So if you want to think about it that way. So that's your charge. And then when you're dividing that again by microcoulombs to find the individual ones, then that's going to put you straight back into volts because the two micros are going to cancel each other. That way you don't have to worry about moving decimal places in different directions and doing stuff like that. But, but yeah. But that's my 2 cents, so I'll leave that out. So it should be fine.
I don't know. Sometimes I'm like, if it works for you, go with it. But sometimes watching your math, even during class, I'm like, this would not work for me if I was solving a problem this way. I'm like, I want numbers in as soon as possible.
Yeah. Well,
And you'll
yeah.
just carrying like the variables down all the way through the algebra. I'm like, I would have lost something by now.
Gotcha. Well, I do that because, for example, the
Like
the example problem we did
plug in
before
the
that, a lot of times
number.
what happens is the C's are canceling and all that different stuff. So there's no point for me to multiply numbers that I don't need to multiply. So that's kind of why I do it. But we're all different. It's fine.
But knowing me, I would have lost one of those C's on the way down anyway. So
Gotcha. But it's okay. You're not the first person in history that wanted to plug in numbers, so it's fine. Yeah, I think the engineering students are actually even worse than you guys are, so it's fine. They love their numbers. So.
I guess that makes a certain amount of sense. If you're going into engineering, you're going to probably be plugging in numbers most of the time. So
Depends on what you're doing, but yes. Yeah. If you're more designing things and, innovating it, then no. But if you're
you're very lucky, the computer's going to do most of it for you.
Well, yeah. Almost everything's going to be computer simulations. So.
Right.
Yeah. Check on the other two. Let me go, Lisa. Oh, she's gone. Okay.
Sent that picture in the text message. Callie, did you get it?
Yes, I did. Thank you. I'm looking at it right now.
Okay.
I actually ended up getting the name for B, so I was fixing it during all your guys' thing, and then we'll see about C if we're gonna try it out.
Okay. I think it was probably just a hiccup in the conversion somewhere then.
So for B1 and B4, did you get 6 volts? And then B2 and B3, did you get 3 volts?
I'm not there yet.
Oh,
Just a
sorry.
second. No, it's fine.
Mhm.
Oh, for C, it's voltages. I was, for some reason, doing charges there.
Oh yeah, so for the charges, I had for the Q1 and Q4, it was the 42 microcoulombs or the 4.
You're plugging that into, you're plugging that into the Q equals C delta V equation.
Yeah, and I'm just dividing, so I'm dividing that by 7, whatever the thing would be to get the volts for it. And then the other ones, I just that added, subtracted by the total voltage because they should add up to equal that.
Gotcha. Oh, we declared C1, didn't we? Oh, it was given. Duh. Losing given information. I'm like, I don't have enough. Do I need to solve for this? No, you already had it.
It happens all the time.
Like in chemistry, they're like, always write down the given information and then what you're trying to find. And somehow So I got 6 volts for V1.
And that should
So
be,
you got,
yeah, and then I got, that would be the same then for like the V4 since they're in.
yeah?
And then in order to find
Okay.
V2 and V3, I
Yeah.
have to subtract the 6 plus 6, so 12 from the 15, because they should all add together.
Right.
So I got 3 volts for those two. I'm not sure if that's right though, but I think.
No, I think you're right. Because then if you, the two that are in parallel, 2 and 3, would be equal to each other.
Okay.
So those would be the same anyway.
Okay.
So we end up with V1 and V4 are the same, and
Yes.
2 and 3 are the same.
Okay. For Q2 and Q3, what did you get for the charge, I guess, for that? Like the charge stored on them?
I haven't made it that far. I declared Q2, 3 to equal the same as 1 and 4, but I'm suspecting that you're going to have to use that other equation again here in a second. Because now that we've found the delta V's, you plug that in to find the charge of each of those.
Yeah.
Those charges will be the same because they have the same capacitances.
For Q2 and Q3?
Yep. Yep. Yeah. If they had different capacitances, then it would be different. But since they're the same, they'll have the same.
Yeah, so I just took the volt for them, like the potential across them, multiplied by like the C, so like that 7 that it gives us in the beginning to find the Q2 and Q3. I'm not sure if that's right.
Oh, the stored energy. Okay, I had written that down wrong. So the part D is potential energy calculations, yeah?
I closed that hand. No, I think it's just potential, or no, charge. Yeah, I don't remember it asking anything about stored energy.
Okay, maybe I'm looking at the wrong question here.
Maybe I posted the wrong one.
For part C, it's the potential across each capacitor, and then part
Right, and then part D is the charge.
Okay.
And yeah, and then that's it. Yeah.
The wrong problem. I have too many of them open.
It happens.
All the circuits look very similar, so you open one and it has a circuit on it. You're like, yeah, that one. Charge. All right.
And that's why I'm trying to go by the title instead of the picture. So.
Yeah.
No.
I'm getting stuck at the just C's calculating the potentials.
Well, once you know the charges, because the charge on all 3 of those different capacitors will all be the equivalent charge.
Right, which is 4 point whatever coulombs. Yeah.
Right. So what you also know is that Q is equal to C times delta V. So that means that delta V across each one then is just going to be equal to that charge divided by the capacitance of each one of those individual capacitors.
Oh, our capacity. So I just go back to like, oh, so why would it? So we just add those together. Hold on. So like Q1 over C1 Let me just show you my screen or my. Can I flip the camera? Is that right?
Well, you just do one. We're not finding VEQ. You just want to find V for each individual one. So what you have is that delta VEQ is equal to each of those individual peaks. But yeah, so just do one at a time. So that means delta V1 is just equal to Q1 over C1.
Okay.
And then delta V2 is, you know, Q1 again because it's the same. Yeah, that's fine. Divided by that capacitance. Good.
Mm-hmm.
And then finally the last one. Okay.
Whoops. That's a 4.
There you go. So Q4 divided by C4.
Okay. And those values are all the same, right? Like C was all just 7.
Well, the only one that's different is the V23, and that's because that capacitance is twice the size of the other ones.
Yeah, because it's added together. Okay.
That's right. So that's right. So delta V1 is equal to delta V4, and then delta V23 is half the size of that.
Because it's C2 plus C3.
Right. Exactly.
Okay. Okay, thanks. I'll get back on that.
Okay. All right. So we are out of time. Actually, we've been out of time, but that's fine. So, good. So everybody have a good weekend. And Monday, we will start making this a little more complicated, but slightly easier at the same time. So we're going to start adding in all kinds of different batteries and things, and it's going to be a jumbled mess, but life will be great. So we're going to start what's known as Kirchhoff's loop rules. So it'll be fun.
Okay.
All right.
Cool. Then I can do the extra credit.
There you go. Well, you can do the extra credit now, actually. Now you have enough
Okay.
with the parallel and series. Well, is that true?
It asks us to use Kirchhoff's, so
Okay.
I wasn't sure.
Yeah, so we'll wait until Monday, so it'll be fine. Yeah, so you can do it Monday.
All right. Okay.
But you can do
Have a
part
good
of it
weekend.
now. So you can actually combine all of those extra resistors down into equivalent resistors. So you can do that at this stage.
Okay.
And then just save the last part for Monday.
Okay, cool.
All right. Well,
Yeah.
have a good weekend, and I will see everybody on Monday.